In this lesson, we're going to take a look at the idea of concavity. Concavity is a mathematical word for examining how your rate of change itself is changing, how the steepness of your tangents is changing. Okay? So if we have a function, goes up and down, okay? Our tangent line right there is a positive number. And move a little higher, it's still positive but less. Move a little higher, still positive but less. Move a little higher, oh, it's zero now. That becomes a negative, a bigger negative, a bigger negative. Oh, back to positive, or sorry, smaller negative, back to zero, positive and positive and positive. By examining the kinds of values you have for your derivative, be they increasing or decreasing, we can get an idea of the shape of our curve. And we call that concavity. So the big ideas for today are, if your derivative is constantly increasing, on that section of your graph, it's going to be concave up, which means it's going steeper and steeper and steeper. If your derivative is constantly decreasing, it's going to be concave down. So it's getting less than, it's going to get steeper and steeper and steeper, concave down. Okay. There are points where it's neither concave up or concave down. We consider those inflection points. So take a look at this picture here for a second. Just going to change colors so we can see a little bit easier. Hope you would agree that it's increasing, decreasing, 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 getting smaller numbers, smaller numbers, smaller numbers, zero, into the negatives now, bigger negatives, bigger negatives, bigger negatives, oh, getting smaller negatives, smaller negatives, smaller negatives, zero, positive, 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 positive. And our tangents is all about our tangents, our slope of our derivative. So for this entire first section up to there, it's concave down. It's going to be less and less and less our slope of our derivative. After the green dot, the point of inflection, our graph is getting, our derivative is getting steeper and steeper and steeper. It's getting to be a bigger number. Started in the negatives, went to zero, and got bigger and bigger until it got to a big positive number. Okay, so the second half of the graph would be concave up. Now, we obviously don't want to have to do graphs and draw a whole bunch of lines on there, though we can, we just did. We want a better idea. So what we use something called our second derivative test, if you will. Okay. So what we want to do here is we want to use the intervals between critical points of your second derivative. In other words, where your second derivative equals zero. If we can find those critical points, those are our inflection points. On either side of those, our function's either going to be increasing or decreasing. And when we're talking about a function, we actually mean our derivative function, right? So it's increasing steepness or decreasing steepness. And the three things you're going to come across are, well, if it's positive, it's concave up. If it's negative, it's concave down. And when we get that f double prime at zero, we got our inflection point. Okay, so we're going to try an example just to sort of hopefully clarify this a little bit for you. So I want to know the intervals of concavity and any inflection points. So we're going to start off by taking our first derivative. So 4x cubed minus 18x squared. Then we're going to take our second derivative. So 12x squared minus 36x. I want to know where my inflection points happen. So I'm going to take my second derivative and I set it equal to 0. So 12x squared minus 36x. And I want to factor that. So 12x, common factor that out, and I get x minus 3. So at x is 0 and at x is 3, something's happening. We assume those will be our inflection points. What happens on either side of those will be our increasing or decreasing concavity ideas. So we're going to make ourselves a sign table. So we're going to go less than 0, and then 0 to 3, and then greater than 3. And I want to know what's happening to my second derivative at those points. So my second derivative, f double prime, will tell me, are we concave up or concave down? So let's give it a try. If I pick a number less than 0 and put it into my function, so let's take the number -1. And we'll just erase these arrows for a second here, as we usually do. We'll get -12 and -4. And together that makes a positive. Okay, which tells me that this function is concave up right there. So when we're less than 0, we're concave up. If we try the next section, pick a number between 0 and 3. So let's pick the number 1. We'll get 12 and negative 2. And 12 times negative 2 is negative, or in our case, concave down. If we try something bigger than 3, let's pick the number 4. We'll get 48, and 4 minus 3 is 1, which is a positive, still concave up. If you want to know what's happening at the inflection points, we can do that. Our inflection points we know are at 0. So let's go back to the original equation, plug in 0, find our point. We'll get 0 and 10. And our other inflection point's at 3. And if we put 3 back into this original equation, so 3 to the 4 minus 6 times 3 to the 3 plus 10, we should get negative 71. Okay, and that's how we can sort of tell what's going on with our function. So if we had to, another way I'm asking you guys to do this, but if you had to, okay, on a graph, so we'll make it scale, 0, 10, and 3, negative 71's down there, okay, we know it's concave up when you're below 0, means our function is increasing all the time. So it's getting bigger and bigger and bigger. Then it goes for a flat spot. Then it's concave down to there. Okay, and then it's going to be concave up again. So concave up means it'd be increasing, actually. Sorry, I put that in the wrong spot. It's an inflection point. So concave down, and then it's increasing. Okay, so this spot here, it goes flat for just a second. Right? It's going down, and then it's going back up again. Kind of hard to tell there where it's changing direction. Much easier in this one. Okay, but that's our idea. Okay. Let's try example B, if you will. So same ideas. I want to find my points of inflection, my concave up, concave down spots, and see what happens. So let's take our first derivative. Y prime is 6x plus 5. Y double prime is 6. I want to know where this equals 0. Well, where does that equal 0? It's the number 6. It can't equal 0. It's the number 6. So what does that tell us? The fact that f double prime is greater than 0 all the time, it's a positive 6, okay, tells us this function is always concave up. That's up because it's positive. Okay. I'm hoping you would recognize what this function is. It's a quadratic. And this quadratic opens up. So if you stop and think about it, every derivative I draw is always increasing in, every tangent I draw is always increasing in its value, right? The slope here might be a big negative, negative 10, then negative 6, then negative 4, then negative 2, then 0, then 2, then 4, then 6, and so on and so on and so on. It's getting bigger and bigger and bigger all the time. It's always concave up. Okay, but I can tell that I use my second derivative test. Okay, let's put it all together now. Stuff we were doing yesterday, stuff we were doing today. Let's make a good sketch, find out all kinds of properties about this lovely function. So I've got a cubic. I want to find the zeros. Okay, so this goes back to last year a little bit in terms of how do we solve for zeros when it's a cubic. We either have to factor it or we have to use synthetic division. In this case, synthetic division makes the most sense. So we need to figure out f at something that comes out to 0. So we have to guess and check a little bit. Try f at 1. Well, that's going to give us 1 minus a plus 12. That doesn't work. It doesn't come out to 0. If we try f at 2, we'll get 8. 8 minus 4 is 4. Minus 16 is negative 12. Plus 12 makes, 0. So we know that that's one of our zeros. So if you recall synthetic division, take your coefficients. Okay, take the 0 we know that works. Put it out front. Okay. We always carry down the first one, and then we multiply. 2 times 1 makes 2, and then add them together. Okay, so we're adding straight down the column. 2 times 1 makes 2, add them together. 2 times negative 6 makes 12, negative 12, add them together, we get 0. So from this, I know that x minus 2 is one of my zeros. Remember, we change our sign from here to here, times, we work, take our coefficients, remember x squared, x, and just the number. So we'll get x squared plus 1x minus 6 equals 0. And then if we factor the inside part, the trinomial, we'll get x plus 3, x minus 2 equals 0. Okay, so we can write down our zeros. That was the first property we were asked for. So we got 2, we got negative 3, and we got 2 again. And if you recall, the fact that we have 2 twice means we have one of those bounces. So it comes down, touches the axis, and goes back up. Okay, what else were we asked to find? We were asked to find next the y-intercept. That's nice. We can find a y-intercept in standard form pretty easily. Okay, so there's my y-intercept. We're going to make a list of these things. Okay, so here's zeros. My y-intercept we just said was 0 and 12. What was next? Okay, the intervals of increase and decrease. We can tell where our function's increasing or decreasing by using our derivative. Okay, so let's take our derivative. So just using the equation from the top, right? So x cubed, that one. So we've got 3x squared minus 2x minus 8. We know we're going to find our max and mins where this derivative equals 0. So let's do that first. So can we factor this? It's a question we ask ourselves. Looks kind of like a complex trinomial, man plus. So 3 and 8 makes negative 24. Add to negative 2. What numbers do that? Negative 6 and 4. Okay, so decomposition, minus 6x plus 4x minus 8. And if we common factor the first half, we get x minus 2. And the second half, x minus 2. So our equation is that. And our zeros are 3 and x equals negative 4/3. And if you're not sure about that one, we take our bracket, we make it equal 0, and then we solve it. Okay, so we know that at 2, oh sorry, I want to put a 3 in there. Sorry, that's a 2. And negative 4/3, we have a max or min. Now I could go through and make a sign table if I wanted to for this, or, because I know I'm going to need it down the road anyways, I can use my second derivative test. My second derivative test tells me what their max or mins, right? So let's take our first derivative and do the second derivative. So we'll get 6x minus 2. I want to know where this one equals 0. So I get x is 1/3. Okay, now that's where my inflection points are happening. I can also use my second derivative for my increase and decrease idea. How do we do that again? We take our critical points from our derivative, so that's these ones, and we plug them into our second derivative. So let's try f double prime at 2. What do we get? We get 6 times 2 minus 2, which is 10. The fact that it's a positive tells me it's a minimum at 2. If we do the same thing, but we'll do the negative 4/3 one this time. We've got 6 times negative 4/3 minus 2. And that's going to give us negative 10. The fact that the negative tells me it's a maximum at 4/3. Okay. If I want to get the actual numbers, the function values, remember we have to go back to the very beginning and figure out what happens at 2 and negative 4/3. So give it a try. If I put 2 in there, oh, well, the good news is, hey, already did that one, right? At 2, we get 0. So it tells me I have a min at 2 and 0. Now, unfortunately, we're not so lucky with the next one. If we put negative 4/3 back in this equation, so f at negative 4/3, if you do it properly, I ended up with 18.5. Okay, so this is back to the original function at negative 4/3. Okay, that's where that came from. Okay, so what have I got now? We got our mins and our maxes. Okay, so what else can we figure out from that? Well, we know it's increasing. Actually, I think it asked us for intervals of increase and decrease, right? Let's see. Yep, intervals of increase and decrease. So add to our list here, and it's increasing. And when's it increasing? It's increasing before you get to a maximum, right? Okay, so it's increasing when x is less than 4/3. Okay, and this can go from a max to a min. Okay, so that would be, it means it's decreasing from -4/3 to 2. What happens after it hits a min? It starts increasing again. So here's my intervals of increase and decrease. Okay, what else were we asked to find? Optimum values, we did that already, our max and min. Intervals of concavity. Okay, we haven't done that part yet. So intervals of concavity, what do we need for that? We need second derivative. We need to know what's happening on either side of our critical points. Now, up here, this was our critical point, right, for second derivative. So we need to know what's happening below 1/3 and what's happening above 1/3 in terms of our second derivative. So let's pick a number less than 1/3. Let's pick 0. If I put 0 in there, I'm going to get -2. If I pick something bigger than a third, pick the number 1, we'll get 6 minus 2, which is +4. So what could I say about this? My concavity, let's concave down and concave up. Okay, so that's some more information we need. What else were they asking us to do? They asked us to inflection points. Oh, okay, inflection points. So what do we got? Where do inflection points happen? They happen at the critical points of our second derivative. So we got an inflection at, let's write out 0, at 1/3, and that's 1/3 because it's this piece right here, right? The critical, that's my point of inflection is. It was going down, then went up. That's right. Down and up. Okay. If I want to figure out what the actual value is, I have to go back to my original function and plug in f at 1/3. Back to the very beginning, right? That's where we get this number. If you do it properly, I got 9.26. So just check yours to see if you get the same thing. And the last thing they want us to do, and there was a lot of stuff in this one, is make a sketch. So let's get ourselves a sketch. Back to the beginning, our list of all the things. What do we know? We know for sure we've got zeros. 2, -3. Let's put those in. We got one at 2. We got one at -3. We knew for sure there was a y-intercept at 12. Okay, so I'll call that 12. We knew for sure we got mins and maxes going on here. We got a min at 2, 0, which I've already drawn, and a max at -4/3 and 18.5. So -4/3 and 18.5 would be about there. -4/3 and 18.5. Okay. I know I've got a point of inflection at 1/3, so that's 1/3, and 9.26 would be about there. What else do we know? We know mins and maxes done. We've got our y-intercept done. We did all that stuff up there. Okay, we'll go down a little bit further. We know it's increasing until it gets to -4/3, decreasing afterwards. Okay, so all we really need to do now is draw our graph, right? So let's talk about that concave up and down stuff. It should be concave down as long as we're below 1/3. So our graph needs to go up and then down. Okay, so what's happening here? Our derivative function, our derivative value at this point would be a really big number, right? At the very beginning here, and think about this down here, really big positive number, less of a positive number, less of a positive number, less of a positive number, 0. Okay, we're going to the negative numbers now, negative numbers now, negative numbers now, until we get to there. Oh, sorry, down here. Once we get to the 1/3, well, now it's starting to be concave up. So it's going to come back down and then bounce off that 0. Okay, so the whole left-hand side of the graph is concave down. Whole right side, concave up on either side of the inflection point. Now, I suppose you don't really need those to graph it. You have all the points and pieces. You have to draw it through them anyways. But just the idea of inflection points in concavity and how they work. Okay. The reason I like those things is we can figure out what's happening in different sections of the graph without having to draw the entire graph. It gives us a good sense of a shape. We can really do that by knowing some things about your derivative and your second derivative, by knowing if it's increasing, decreasing, and concave up and concave down. So here's some rules, some ideas for you. If your graph is concave up and it's an increasing function, it has to look like this. It's getting steeper and it's going up. If it's concave up, so it's getting steeper, but it's decreasing, it has to look like this. And the numbers have to be getting bigger, right? So they start off by being big negative numbers, and then smaller negative numbers, and smaller and smaller and smaller until eventually you can get to 0. Okay, but it also has to be going down. If it's an optimal value in concave up, well, it's got to look like this. Okay, it has to have the flat spot on the bottom of it somewhere in there, right? And concave up means our values have to be increasing the whole time. We'll try the next set of groups. Okay, if it's going to be concave down, but an increasing function, it means it has to be increasing, but at a decreasing rate. Going to kind of look like that. Concave down and decreasing, so decreasing at a increasing rate. Going to look like this. And concave down, but an optimal value, well, that's obviously the opposite version, right? Okay, the last set is what happens when you have an inflection point. Well, if it's an increasing function with an inflection point, that means it's got to go up and up. It's got to have the flat spot right in the middle. If it's a decreasing function with an inflection point, it's got to go down and down, and again, a flat spot in the middle. And so by using these sort of ideas, these pictures here, we can get an idea of a shape, not necessarily the entire shape, but just knowing a little bit of a shape in an area. And we call this sketching in the neighborhood. And by taking our first and second derivatives and knowing something with their values, we can get a sketch in the neighborhood, so near points without knowing the entire function. So we're going to try a couple. So a section of a function. So what do we know? We know that the function has a value at 2 of -5. This is the point. So 2 and -5. We know that the derivative at 2 is a positive 10. That means it's increasing. We also know that the second derivative at 2 is -3, which means it's concave down. So I need a function that's increasing, but concave down at that point. What does that have to look like? So it's got to be an increasing function at a decreasing rate. So I know it's got to go like this. It's going up, but it's not going up as steep as all the time. It's getting less and less steep. And if we try the next one. The point is -1 and 4. That's right there. The derivative is 0. That tells me it's a max or a min. Okay? And I know that it's a concave up because my second derivative is positive. So it's going to be concave up at that point and be a max or min. Got to look like that. No choice. And we'll try the last one. So we've got 3, -3. That's that point. We know it's a decreasing function because my derivative is negative. And we know our second derivative is 0, which means it's an inflection point. So if it's decreasing and it's an inflection point, it's got to go flat for a second and continue on. And there's just 3 graphs. We call this sketching the neighborhood, just identifying some small properties. Okay, here's your last one, last idea for today. Can you figure out for me the signs, don't care about the numbers, but the signs of your function, your derivative, and your second derivative at each of the points A, B, C, and D? So here's what we're going to do. Let's make a table. So I want to know A, B, C, and D. And I want to know what kind of signs our function has, our derivative has, and our second derivative has. So basically, are we increasing, decreasing, positive, negative, all that good stuff. So let's find A. What kind of sign does A have? Well, it's a positive value, right? Positive 5. So, okay, positive. At A, is the function increasing or decreasing? Well, for me, it's not doing either of those. So we're going to put a, oops, sorry, not dash, a 0 in there. Okay, it's not increasing or decreasing at the point. It's a maximum. Our second derivative, what's it doing? It was steeper, and it's getting less steep and less steep and less steep and less steep, so it's negative. Okay, let's try the next one. B. B is at 3. Okay, so that's positive. The function looks like it's going down at that point. Okay. What's happening here, this is a little tricky, this one, is that increasing, is that decreasing? So I was here, then I was here, then I was here. A little tricky to tell. I don't really know if that's an inflection point or not. I'm going to go with the fact that it's a negative. That's the one judgment call you're going to have to make at times. Okay, I'll try to make them pretty obvious for you guys if it's an inflection point. Let's try C. C is a negative value. The function is still decreasing at that point, but it looks like my tangent is starting to get steeper, so it's a positive. And D, well, D is obviously negative. The function is just started to increase there, it looks like. And my derivative was at 0, and now it's starting to get bigger again. It looks like it's a concave up situation. Okay, so that's the kind of thing I want you to do. You try the last one. The same idea, so you make a chart. So A, B, C, D, function, derivative, second derivative. Okay, what do we see at A? A, let's do all the function values first. So A is a negative, B is a negative, C is a positive, D is a negative. Okay, first derivative. What's happening with A? What's going down? B is going up, C is going up, and D is going up. Okay, and then we talk about concavity. So as we approach A, what's happening? It's getting steeper and steeper and steeper. Okay, so it's negative. B, we were steep, we're getting less steep. So it's increasing. Oh, sorry. B is decreasing. Okay, we were steep, we're getting less steep, right? C, we were here. Now it's getting steeper, so it's a positive. And D, we were here at the big number, less of a big number, less of a big number, less of a big number, so it's a negative. Okay, there's your idea of concavity for today. We should be able to make sketches in the neighborhood, figure out different signs of things, and put it all together and make a big drawing. Okay, the homework today is just from this lesson. Here's the 3 questions I want you to try. And if you could, page 206, number 10. Okay, that's the end of that lesson.